Swayam Prabha. Digital India. Educated India.
Welcome to the second lecture of the lecture series on tutorials on design of transmission elements. This second lecture is on tutorial on design of the spur gears. In the first class we studied about the problems related to basics of the spur gear and the force analysis of the spur gear. Now, in this lecture, we will take problems related to design of the spur gears. The problem which we are going to take is a design a 4:1 spur gear reduction for a 75 kilowatt 3-phase squirrel cage induction motor running at 18.667 revolution per second. The load is smooth. The information about the source is given. So, this is here the source prime mover will be connected. So, the information given is it is smooth, and this will be used to determine the overload factor, providing a reliability of 0.95. Reliability given is 0.95. The strengths, the fatigue bending strength and the surface fatigue strengths are given for 0.99 reliability, and so we have to use a reliability correction factor. The life required is 10 to the power 9 revolution. 10 to the power 9 revolution is the life for the pinion. Now, we know that the strengths, the AGMA strengths are given for 10 to the power 7 number of cycles, and so we have to use life factor also. The gearing space is meager. It means we have to design a gear with a smaller size, and the material of the gear and the pinion is nitrile alloy 135M grade 1 material. Now, this data will be used to determine the strength of the material of the pinion and gear. Now, the stresses in the spur gears, what type of stresses acts on a spur gear when power is transmitted from one gear to another gear? There are two modes of failure. In the figure, those two modes are shown. The first one is fatigue fracture due to bending stress. Tangential force acts at this point, at the highest point of single tooth contact, and due to this at the root the bending stresses acts, and the gear may fail due to this bending fatigue. So, the first one is fatigue fracture due to fluctuating bending stresses at the root of the tooth. They are fluctuating because when the tooth will be under engagement, these stresses will act, and they will disappear, will become 0 when the gear tooth will disengage. The next one is the surface fatigue, as the gear tooth are contact at this point. This is the mating gear tooth, and so very high contact stresses acts, and those contact stresses are determined from the Hertzian contact stress. These are also fluctuating because when gear tooth will be under contact, they will be there, and when the gear tooth will disengage, they will become 0. So, the second type of stresses which acts on the gear tooth, which is under engagement, is Hertzian contact stresses, which produces surface fatigue, which is also called the pitting of the tooth surfaces. So, the determination of this bending stress and determination of this contact stress is very important. and those stresses will be compared with the strength of the gear material under bending and contact stresses. And the developed stresses will be compared with these bending fatigue strength and the contact strength. Now, ferrous materials have bending endurance limit. Materials do not exhibit an endurance limit for repeated surface contact stresses. Now, what is the design objective? Let us study in brief. The resulting drive should be, in this figure, a shaft, driving shaft and driven shafts are shown. If this is the driving shaft and this is the driven shaft, these shafts are supported by bearings. So, the complete set should be compact and small, operate smoothly and quieter, have long life, be low in cost, be easy to manufacture, be compatible with the other machine elements in the machine. That means the drive should be compatible with the bearing, with the shaft, the housing, driver and the driven machine. In bending, the AGMA equation are displayed side by side. The bending stress is given by this equation where Wt is the transmitted load, F is the face width of the gear, Mt is the, in the case of a spur gear, it will be simple M and that will be the module, J is the geometry factor and it will be different for the case of pinion and gear. And so, here when we are determining bending stress for the pinion, it is Jp. Then there are different factors, correction factors, and they are velocity factor, overload factor, mounting factor, size factor, the rim thickness factor and the idler factor. For the case of gear, the same is given. The only difference will be in the geometry factor for the bending, it will be Jg, and the size factor for the gear, it is Ksg. For the case of pinion, it is Ksp and Jp. Rest all are same for both the cases. Strength of the material against bending fatigue is given by, this strength is determined from the AGMA material data, and that is for 10 to the power 7 number of cycles, reliability equal to 99% and temperature less than 120 degrees centigrade. Now, if you want to design your gear for life other than 10 to the power 7 number of cycle, reliability other than 99%, temperature more than 120 degrees centigrade, then this fatigue, bending fatigue strength should be corrected by multiplying it by the life correction factor, dividing by the temperature factor and the reliability factor. And so, the corrected bending fatigue strength for the pinion material is given by this one. Similarly, for the case of gear, it will be like this. The life factor for the pinion and the life factor for the gear will be different. The temperature and reliability factor will be same for the gear and the pinion. Factor of safety under bending for pinion and gear will be determined by ratio of the bending fatigue strength and the bending stress, and that is given by this, and it is defined by NB pinion and NB gear. Similarly, for the case of contact stress, the contact stress is given by Cp, which is the elastic constant, and there is a table which gives us the value of this Cp. Otherwise, if we know the Poisson's ratio of the material of gear and pinion and the elastic modulus, Young's modulus for the gear and material, we can determine the value of Cp. Wt is the transmitted load, F is the face width, dP is the pitch circle diameter of the pinion, I is the geometry factor for the surface fatigue, and the factors are same, correction factors are same as were used in the bending determination of bending stress, and it is to the power half. And so this sigma c contact stress is related to under root of the transmitted load, whereas sigma b was related to Wt. This sigma c is related to under root of the Wt, and this will be used in determination of the factor of safety. Similarly, surface stress for the case of gear is given by this one. The only difference will be the geometry factor for the pitting resistance. Here it will be Ig, and the size factor for the gear, which will be Ksg. The strength of the material under surface fatigue is determined from the data sheet or the data book, AGMA data given, and this is again for 10 to the power 7 number of cycles, reliability equal to 99% and temperature less than 120 degrees centigrade. Now, if your gear has to work under circumstances other than these, then you have to multiply it by life correction factor CL and divide it by temperature factor TL and reliability factor TR. Similarly, for the case of strength of the gear material under surface fatigue is given by this formula. Here one factor is remaining, which is the hardness correction factor. This is called the hardness correction factor. And the factor of safety against contact stresses for the case of pinion is the ratio of surface fatigue strength of the pinion divided by surface contact stress which acts on the pinion. Similarly, the surface factor of safety for the gear material can be determined. Now, this factor of safety is with respect to under root of the Wt, and so for when we compare the factor of safety against bending fatigue, that is Nb, with this Np, then for comparison this Nc is made square, so that both are related to Wt and Wt. And then the factor of safety against bending and factor of safety again against contact stresses are compared. A useful decision set for spur gear includes a priori decisions, which are function, load, speed, reliability, life and the overload factor. Then for unquantifiable risk, we take the design factor or factor of safety, and the tooth system, which is the pressure angle, the helix angle for the case of helical gear. For the case of spur gear, this will not be taken. Then the addendum, dedendum, root fillet radius. Then gear ratio mg, which is the this mg is the ratio of number of teeth on the gear divided by number of teeth on the pinion. So, this must be known a priori. So, these are the a priori decisions. Then number of teeth on the pinion, number of teeth on the gear, and these should be selected taking care of the interference. Then based on these a priori decisions, we take the decisions which are the quality number of the gear and pinion, then the module, then the face width, pinion material with its core hardness and case hardness. Core hardness and case hardness means case hardness are done for the surface fatigue, and this will be under certain depth from the surface, and the core is within the material what is the hardness. So, this is your core hardness and this is your case hardness. So, that we have to select. Then the gear material, its core hardness and case hardness. Now, the steps after a priori decisions have been made are: choose a module based on the preferred numbers and the next choice, Then examine implications on the face width, pitch diameter and material property. If not satisfactory, return to pitch decision for change. Choose a pinion material and examine core and case hardness required. If not satisfactory, return to pitch decision and iterate until no decisions are changed. Choose a gear material and examine core and case hardness requirement. If not satisfactory, return to pitch decision and iterate until no decisions are changed. Now, with these plan steps in mind, we can consider them in more detail. First, select a trial module. If in your problem module is given, then this step is not required. Then pinion bending is checked. Then gear bending is checked. Then pinion wear is checked, and the gear wear is checked. Now, for our coming to our given problem, the priori decisions are function. In the problem, it is given that we have to transmit power 75 kilowatt and the pinion has to run at 18.667 RPS. Required reliability is 0.95. Life required for the pinion is 10 to the power 9 cycles and the drive is smooth, and so the overload will be 1. Design factor for is taken as 2, and the tooth system, the pressure angle is taken as 20 degree. Pressure angle is taken as 20 degree. Tooth count, number of teeth based on this pressure angle, which is interference free for the pinion, is 16, and as our velocity ratio or the gear ratio is 4, the number of teeth on the gear can be taken as 16 multiplied by 4. But let's take number of teeth on the pinion as 18, and so number of teeth on the gear will be 18 multiplied by 4, that will be 72, and there will be no interference. The quality value is taken as 1 and the grade 1 material is used of nitrile oil. Now, assume MB, which we will deal in when we will discuss about the rim thickness and the effect of rim thickness. Okay. Then selecting a module equal to 6, that means our first step will be for selection of the module, and the module is selected from a table which just we discussed, and from the first choice we have taken 6 mm as a module. Knowing the module, now we can find the pitch diameter of pinion and gear. The pitch diameter of this is the pitch circle of the gear. The pitch circle diameter is this one, and this is given by dP. So, if I make it by green color, then pitch circle diameter is this one, and it is dP. And knowing the module, we can find this because module M is given as pitch circle diameter D divided by number of teeth. So, to get the pitch circle diameter of the pinion, this D will be written as dP and Z will be written as ZP, and thus dP is equal to ZP multiplied by module, and the pitch circle diameter of the pinion has come as 108 mm. So, this is 108 mm. Similarly, the pitch circle diameter of the gear is number of teeth on the gear multiplied by module. Module will be same for both pinion and gear, and thus it has come as 432 mm. It means DG is 432 mm. Now, let us find the pitch line velocity. This is the pitch point where the pitch circles are tangent to each other, is the pitch point. The centers are, center of rotation is O1 and O2. So, where O1 and O2 intersects the pitch circles, this is called the pitch point, and corresponding velocity is called the pitch line velocity. And this is given by pi, pitch circle diameter of the pinion, number of revolution of the pinion, and this is in RPS, revolution per second, divided by 1000, because dP is in mm and we want to get pitch line velocity in meter per second. Substituting the value of dP and nP, the RPS of the pinion, we get the pitch line velocity. Now, knowing the pitch line velocity, we can find what load will be transmitted or what force will be transmitted when this pinion will run with this speed. Well, and the transmitted load is the Wt, which will drive the gear. So, the transmitted load is given by the power which you want to transmit divided by the pitch line velocity, and the power is 75 kilowatt, and so 75 multiplied by 10 to the power 3 is in watt divided by pitch line velocity in meter per second. We determined the transmitted load, the force which will be transmitted when this pinion will run at 18.667 RPS. So, this is your Wt. Now, in bending, the AGMA equations are displayed again. Now, we have determined this Wt, and the face width is not given in our problem. This module is, we have selected as 6 mm. Now, we have to determine one by one the value of Jp, the geometry factor, velocity factor, overload factor, mounting factor, or the load distribution factor, size factor, and the rim thickness factor, and the idler factor. And for the case of strength, we have to find from the AGMA materials data the bending fatigue strength, and then it will be corrected for our life, and so we will determine the life factor, and then the temperature factor and the reliability factor, because reliability required is other than 99% and the life required is other than 10 to the power 7 number of cycles, but the temperature is less than 120 degrees centigrade, and so it will become equal to 1. And thereafter, we will determine the factor of safety against bending fatigue for the pinion and for the gear, this and this, by taking the ratio of corrected bending fatigue strength for the pinion and the bending fatigue stress which is acting on the pinion. And for the case of gear, the factor of safety against bending fatigue for the case of gear will equal to the bending fatigue strength of the material of the gear divided by the bending stress which acts on the gear here, and these two will act along the route, along this. For predicting surface fatigue failure, the equation for surface stress and surface fatigue strength are given below this, and the factors we have to determine. Now, the first is in the bending fatigue, determination of geometry factor. Geometry factor is determined with the help of a figure which is shown here. On the x-axis is the number of teeth for which geometry factor is desired. So, if we want to determine geometry factor for the pinion, then number of teeth on the pinion was selected as 18, and so corresponding to 18 we will find the geometry factor J. And when we are going to find the geometry factor for the gear, the number of teeth on the gear is 52, and so 52 will be selected. Let us see. Zp and ZG are 18 and 72. And so, for the pinion, we will select 18 number of teeth, and the corresponding geometry factor is 0.309 here, 0.309. For the case of gear, number of teeth is 72, and so corresponding to 72, and number of teeth on the mating gear is 18. So, a curve corresponding to 18 will be somewhere here, and so what actually we do is we determine the J corresponding to 17 number of teeth on the mating gear and 25. These two curves are given, and then we just interpolate to get the value of JG corresponding to a curve which is not given. So, there is no any curve for the mating gear equal to 18, because when we are going to determine JG for geometry factor for the gear, then number of teeth on the gear is 72 and number of teeth on the mating gear is 18. And so, a curve corresponding to 18 should have been selected, but there is no curve corresponding to 18, and so we will find a value of JG when number of teeth on the mating gear is 17 and when number of teeth on the mating gear is 25, and then it is interpolated to get the J for the gear when number of teeth on the mating gear is 18, and it has been found as 0.4324. It is 0.4324 by interpolation. So, we got the geometry factor for of the bending stress equation for the pinion and the gear. Now, this may also be obtained from the AGMA table, where on the first row is the number of teeth on the gear. Our case is 72. So, again there is no any value, and so it will be interpolated, and number of teeth on the pinion is 18. Again there is no any value, and so it will be interpolated. So, for this particular case, the previous method is obtained. The figure was used to determine the value of JP and JG. Now, the next factor of the bending stress equation is the velocity factor. Now, the velocity factor accounts for the factor that the load is assumed by a tooth with some degree of impact, and that the actual load subjected to the tooth is higher than the transmitted load alone. That means, the actual bending stress equation was obtained considering the static case. Now, the gear drive is not a static case, it has certain pitch line velocity, and for the case of spur gear, the engagement and disengagement are which impact. So, the static case is not there, and so we have to take consideration of the velocity factor or the dynamic factor. The value of Kv depends on the accuracy of the tooth profile, the elastic properties of the tooth, and the speed with which the tooth comes into contact. And it may be obtained from these formulas, but we are going to use the AGMA procedure, which is based on quality number. These numbers define the tolerances for gears of various sizes manufactured to a specified accuracy. Quality numbers 3 to 7 will include most commercial quality gears, and thus we have selected QV equal to 6. Quality numbers 8 to 12 are of precision quality. The AGMA quality accuracy level number QV could be taken as the same as the quality number. The following equations for the dynamic factor are based on these quality numbers. The velocity factor or the dynamic factor is equal to A plus under root 200 pitch line velocity divided by A to the power B, where V is in meter per second, which is the pitch line velocity, and A is given by this formula and B is given in terms of quality value. So, knowing the quality value, we will determine the value of B. Our quality value is 6, and then we will find the value of A, and A and B will be substituted in this equation to get the value of Kv. There is a figure also based on the pitch line velocity in meter per second and the curve corresponding to the quality value. We can also find the value of Kv, but we are going to use the formula. Therefore, to get the velocity factor Kv, we first determined the value of B by using quality value Qv is equal to 6, substituting the Qv equal to 6, and then A by substituting B in this place, and we got A as 59.77. Putting the values of A, B and pitch line velocity in this equation of Kv, we get the value of Kv, the velocity factor, as 1.47. And the pitch line velocity was calculated earlier and it was 6.33 meter per second. The overload factor, it was given that the drive is uniform. So, if the source of the power is uniform and the driven machinery is also uniform, then the velocity factor is 1. Now, depending on the source of power and the driven machine, we will get the value of Ko for other cases, but our case the Ko is 1. Then the load distribution factor or the mounting factor Km. In the bending stress equation, we have to find the value of this Km, which is the load distribution factor. This factor accounts for distribution of load along the width. In the original Lewis equation, it was assumed that the distribution of load is uniform throughout the width, but due to various reasons, the distribution may not be uniform, and that we may account during determination of bending stress. The procedure is applicable to this following case, and we are going to use it, and the load distribution factor is given by this formula, and in this formula number of factors are there. So, one by one we are going to determine all these factors to get the value of Km. The first one is CMC. CMC is equal to 1 for the uncrowned teeth. The uncrowned teeth is this one, and the crowned teeth is this one. Now, considering uncrowned teeth, for the uncrowned teeth CMC is equal to 1, for uncrowned teeth it is 0.8. Now, considering uncrowned teeth CMC is equal to 1. Then next factor is CPF of the mounting factor or the load distribution factor. It depends on the face width and the pitch circle diameter. Now, the if face width is 75.4, which is the mid range of the face width, because face width should be greater than or equal to 3 pi multiplied by module, and it should be less than or equal to 5 pi module, and we had selected face width as a mid value, and that is 4 pi m, and this is only for determination of the Km. Later on we will find the this face width considering the bending fatigue and surface stresses, and then again we will modify this Km based on the final value of face width. So, with this face width corresponding to 4 pi m, substituting the value of m is equal to 6, it comes as 75.4 mm. So, and dp is pitch circle diameter of the pinion is 108, and so f divided by 10 dp is 0.06, it is greater than 0.05, and when it is less than 0.05, then f divided by 10 dp is taken as 0.05, but in our case our f divided by 10 dp is more than 0.05, and so this value will be taken as 0.0698. Now, based on the face width, we have to get the value of this CPF. Our face width is 75.4 and which ranges between 25.4 mm to 1000 mm, and thus we will use this formula to get the value of CPF. Otherwise, based on the face width, we either of this or this should have been taken. So, CPF factor is given by from this formula. Substituting the value of f, we get it as 0.094. So, the next thing will be determination of this CPM. Now, CPM depends on what type of mounting is. This is the shaft and these are the bearings, and the gear is mounted like a simply supported beam, and this is the mid of the support, midway. From the midway, the gear is mounted at a distance of S1, and S divided by 2 is the mid length of the shaft, and the distance between the bearings is S. Now, based on S1 divided by S, either it is less than 0.175 or greater than or equal to 0.175, we have the values of CPM. Now, considering S1 divided by S less than 0.175, our CPM is equal to 1. Now, the next is CE. CE is 0.8 for gearing adjusted at assembly, or compatibility is improved by lapping or both, and 1 for all the cases. Let we are taking this one, and so the CE is equal to 1. Now, the next factor is CMA. CMA is given by this formula, A plus B face width plus C face width square, and this A, B, C are given in this table. Based on the condition, either it is open gearing, commercial enclosed unit, precision enclosed units, extra precision enclosed unit, we will get the value of A, B, C. Now, selecting commercial enclosed unit, the value of A and B are given by this red color fonts. Substituting this A, B and C in this formula and F, we get the value of CMA, which is equal to this one. Then finally, we have the Km. After substituting all the constants CMC, CPF, CPM, CMA, CE, we get the load distribution factor or the mounting factor is equal to 1.244. The next is the size factor. Size factor is given by 0.904 Fm under root y. This y is the Lewis form factor. Lewis form factor, and this is determined from this table based on number of teeth. So, to determine the y for the case of pinion, the number of teeth is 18, and so y is 0.309. The face width is taken as this 75.4, and Ks for the case of pinion is your 0.904, the face width, then the module, then the y for the case of pinion. In a similar way, we can find the yg, the Lewis form factor for the gear, considering number of teeth equal to 72 by interpolating the two values, this value and this value. Well, then the rim thickness factor. Rim thickness factor depends on the value of MB, which is equal to thickness of the rim if the gear is made on the rim, not on the solid blank. Then the rim thickness is TR and the total height of the gear tooth is HT. So, the ratio is TR divided by HT. If TR divided by HT is greater than 1.2, is greater than or equal to 1.2, the meaning is TR rim thickness is greater than or equal to 1.2 times the HT. Then there will be no rim thickness effect. What happens is, instead of failure of the gear tooth, the rim fails. The MB should be taken as more than 1.2, and the HT, the total height, is equal to addendum plus dedendum, and for our case it is 13.5, and so the rim thickness should be more than 1.2 multiplied by this HT, which is 16.2. So the rim thickness shall be more than 16.2. Now in our case, for the case of pinion was made on a blank, and in the case of, for the case of gear also, we will ensure that TR is greater than 16.2 and thus KB is equal to 1. The idler factor is for the case of idlers. That means if the drive is based on pinion, idler and the gear, then the idler is subjected to two-way bending like this. Idler is two-way bending, but the gear and the pinion are subjected to one-way bending. So to account for this, the idler factor are taken. For our case, our pinion and gears are not idler, and so idler factor will be 1. And thus, we determined all the factors related to the bending stress for the case of pinion. From this, we can get the value of our F bending because it is unknown. Now, next is determination of contact stress. In the determination of contact stress, the factors Kv, Ko, Km, Ks, Kb, Ki all are same, which were just determined for the case of bending stress. We have to find only this Cp and the I, the elastic factor and the geometry factor for the pitting resistance. And those are, the Cp is determined from this table. For the case of steel pinion and steel gear, the value is 191 megapascal to the power 1 by 2. And so, for our case it is this one. For other cases, this table may be referred. So, I is, the geometry factor is given by sin phi t cos phi divided by 2 mn. For the case of spur gear, mn is equal to 1, the load sharing ratio. Mg is the velocity ratio. For our case it is 4, and thus I is 0.129. So, we have determined all the factors of the surface stress for the case of pinion and gear, and we have Wt is equal to 11848, the transmitted load, and the module is 6. So, knowing the Cp, I, Jp and Kv, we can find the surface stress acting on the pinion, but face width is unknown. So, our next aim is to determine this face width under wear after knowing the surface fatigue strength of the material of the gear. So, strength of the material against bending fatigue is given by this formula. Let us find these factors and this value. The through hardening process is generally used for gears that do not require high surface hardnesses. 4 different methods of heat treatment are primarily used for through hardened gears. In ascending order, they are tabulated here. The reliability factor is determined from this formula. For our reliability of required reliability of 0.95, the reliability factor is this one. The life factor KL is determined from this figure. The required life is 10 to the power 9. So, corresponding to 10 to the power 9, and in the problem it was given that use the upper table. So, selecting the upper table and the formula corresponding to this, we will get the value of the life factor. So, life factor for the pinion is 1.3558, the required life 10 to the power 9 to the power minus 0.0178. For the case of gear, the life required will be life of the pinion divided by the gear ratio. Gear ratio is 4, and so life factor for the gear is 0.961. Now, the material which we are going to use for the pinion and gear are the nitrilloy 135M, and for that the core hardness range is 32 to 36 HRC on the C scale, Rockwell hardness, and in the Brinell it comes to 302 to 335. So, choosing mid-range hardness as attainable using 320 Brinell. For nitrialloy, we have to use figure C to get the bending fatigue strength. So, figure A is for through hardness gear, figure B is nitride through hardness hardened gear, steel gears. Ours is a nitriding gear, and for nitrialloy and grade 1 we have to use this curve corresponding to the core hardness. Now, the formulas, the best fit formulas are for nitrialloy grade 1, the formula is this one, 0.598 Hb, the Brinell hardness of the material. We have taken it as 320. So, we will substitute here 320 to get the bending fatigue strength. So, we got the bending fatigue strength with this formula, and this is for 10 to the power 7 number of cycles, 99% reliability, temperature less than 120 degree, and thus it comes as 278 megapascal. Now, it will be corrected with the help of the life correction factor, temperature factor, and the reliability factor, which we have already determined. So, for the case of pinion, we have bending stress, and this is the bending fatigue strength, and taking given factor of safety as 2. Using all this, we get the F corresponding to bending, and F bending is this formula using this equation, and this. Substituting the factors, we get face width considering bending is equal to 93 mm. In a similar way, the life factor for the surface fatigue strength is determined corresponding to this 10 to the power 9, and that is 0.9 for the pinion and 0.929 for the gear, because for the case of gear, life required is life of the pinion divided by gear ratio. So, the F wear is determined from the equation number A, equation number B, and equation number C. The surface stress, the surface fatigue strength, and the factor of safety against surface fatigue. Using this formula, we get the face width required considering wear. Substituting the all factors, we get F wear as 103.8 mm. Now, the two face width obtained is 99 mm, and the F wear is 103.8. Then the decision is taken as make the face width 105, more than this one, and correct the value of Ks and Km, the size factor and the mounting factor, with the new value of F, and the new value of Ks is obtained at this, and Cpf is obtained as this, and so Km is 1.289. So, with the new value of Ks, new value of Km, and the selected value of face width, now we will find the sigma b of the pinion, sigma b of the gear, and sigma c of the pinion, sigma c of the gear, and the surface fatigue strength SFC, and the bending fatigue strength SFB. And then the factor of safety will be determined by dividing the strength with the stress. So, those are done in these slides. The new value of for the pinion tooth in bending, the allowable stress or the bending fatigue strength, bending fatigue strength is given by this one, and the bending stress which will induce is given by this one, by substituting the new value of face width, new value of mounting factor and the size factor, and it comes as 137.3. And so the factor of safety against bending for the case of pinion has come as 2.145. Similarly, for the case of gear, the surface fatigue strength is obtained, which is 302 megapascal, and the bending fatigue stress with the new value of Km and Ks is obtained as 105.9. Here the strength stress, bending fatigue stress acting on the gear is obtained as bending fatigue strength of the pinion divided by geometry factor of the pinion divided by geometry factor of the gear, and it has come as 105.9 megapascal. So the factor of safety against bending for the case of gear is equal to bending fatigue strength of the gear divided by bending stress on the gear. This value divided by this value, it comes as 2.85. Now the surface fatigue strength of the material of the pinion and gear is obtained from this table, which gives us the surface fatigue strength for 10 to power 7 number of cycles, reliability equal to 0.9 and temperature less than 120 degree. Our material is nitrialloy 135 M, and the surface fatigue strength may range from 1170 to 1350. Let us select surface fatigue strength uncorrected based on these values is 1172 megapascal. So it is corrected to get the value of actual corresponding to our life equal to 10 to the power 9, reliability equal to 95 and temperature less than 120 degrees centigrade. So surface fatigue strength of the material of the pinion has come as 1191, and the surface stress which is acting on the pinion is 841, and thus the factor of safety which is squared so that it can be compared with the WT, because NC, factor of safety against contact stress, is related to under root of the WT as we discussed in our beginning of the class. So this factor of safety of the pinion against wear square is equal to 2. Similarly, for the gear tooth, the material is same, the only difference is the life factor, and it will be multiplied to the hardness correction factor also. So hardness correction factor is taken as 1. The surface fatigue strength of the gear material has come as 1230 after correction. That means taking account of 10 to the power 9 number of cycles divided by mg cycles, and reliability equal to 95%. And the stress which is acting will be same. The contact stress which acts on the pinion and gear are same, and so sigma c pinion is equal to sigma c gear. Sigma c pinion was obtained as 841, and so sigma c gear is also equal to 841. So factor of safety against contact stress of the gear square is equal to ratio of this one divided by this one, and it has come as 2.13. Now what should be the rim thickness? The gear pitch circle diameter is very bigger, and so it will be not made as a blank, but it will be cast with a rim. So we will keep MB greater than 1.2, where this MB is the ratio of rim thickness divided by the height of the gear tooth, HT, which is equal to the addendum height plus dedendum height. So, for our case, module is taken as m, and so the total height ht will be 2.25 times module, and it comes as 13.5 mm. Now, we have to keep this mb more than or equal to 1.2. That means Tr, rim thickness, divided by ht should be greater than or equal to 1.2, and ht is 13.2, and so the rim thickness should be greater than or equal to 16.2 mm. Now, in the design of the gear blank, be sure the rim thickness exceeds 16.2 mm. If it does not, review and modify this mesh design. Now, if we compare the factor of safeties which has been obtained for all the cases, then factor of safety for the gear against wear is 2.12, and in the beginning we has taken as design factor equal to 2, and so the factor of safety of the gear against wear is 2.12, which is slightly more than the required one. So, if we want to make just equal to 2, so we can take many decisions. That means the design decisions were taken for the module, it was taken as 6. We can change the value of module so that this design factor comes as 2, or we can change the material. The materials, it is the surface stress or related to surface strength, and so the case hardness can be reduced. Now, let us see the other factor of safeties. Under wear, the pinion has attained the 2 factor of safety, but for gear it is more. So, we may slightly reduce the your case hardness of the gear. Let us take the bending. For the case of bending and for gear, factor of safety is 2.85. This is again slightly, not very much more than the required. So, we can take decision about the module, or we can change the core hardness. To make it equal to 2, we have to increase this one, and this can be increased by increasing the decreasing the face width, and others, or we can decrease the strength, and strength can be decreased by decreasing the core hardness. In a similar way, if we see the factor of safety against bending for the case of pinion, it is 2.145, and the required one is 2, and so it is slightly more. So, it can be accepted, or if we want to make it equal to 2, then either we can decrease the strength or increase the stress. So, we got the different parameters for the case of given problem. The module which we obtained is 6, which is giving satisfactory factor of safety for the case of pinion and gear under bending and surface fatigue. And the the given material was nitrile 135M, and the its core hardness was taken as 320 Brinell, And with all these selected values, we got a satisfactory factor of safety of the pinion and gear against bending and wear. Therefore, we can say that the gear is designed with module equal to 6, face width equal to 105 mm, and the material is nitrialloy 135 M with core hardness equal to 320 Brinell. Thank you.